Loud and clear. Well, hello to everybody this very sunny day in Sevilla. During the last week we have had very good weather and very clear days without clouds. This has not been the the normal situation during the last few months, which we have had unusually cloudy and rainy weather. And this evolution of the weather during the last months in Sevilla illustrates how difficult it is to assess the solar resource in general. Well, today in this webinar, I will try to make an introduction to the topic of solar resource assessment. The time is too short for going into details, but I hope my intention is at least to give a broad view of some of the important factors in making a good solar resource assessment for a CSP project. Of course, some of these topics or factors are common to any other technology. For example, you need also to make solar resource assessment for PV plants. There are some differences, of course. Perhaps it's a little bit more difficult for CSP, as we will show in a few minutes, but well, many factors are common to both of these technologies and to solar energy projects in general. Well, we'll first start by describing a little bit what is the solar resource for CSP plants. We already talked a little bit about this in the first session, but just I will give just a very short review. Then I will talk a little bit again about the measurement of solar radiation and some ways to estimate it when measurements are not available. I will talk a little bit too about solar radiation databases, about some of the solar radiation databases which are available and can be used for this for making a solar resource assessment. And I will also talk about the statistical characterization of the solar resource and the concept of typical meteorological years and design years in a very short, well, not without going into details, as I said, because time is too short, but I will try to talk a little bit about that. And finally, I will try to give some guidelines for a good solar resource assessment for a CSP project. Well, first of all, the energy source is the sun. In this slide, we have some characteristics of the sun. Some of them are of interest for CSP, like, for example, the angular diameter of the sun as seen from the Earth, as we talked in the first session, or the equivalent temperature, but also the power and the radiance emitted by the sun. The radiance emitted by the sun is 6.35 times 10 to the 7th watts per square meter. However, when the solar radiation reaches to the top of the Earth, the atmosphere, the radiance is significantly less. In this slide, we can see in the red line the solar spectrum, the extraterrestrial solar spectrum on top of the atmosphere before any interaction of the solar radiation with the atmosphere. Well, this data, the reference for this data is here. It's from 1985, but it must not have changed much during these years. And And we can also see that the emission spectrum of a black body at 5777 Kelvin is similar to this extraterrestrial solar spectrum, having the same irradiance. The integral of this curve over the whole spectrum is takes the same value, which is 1367 watts per square meter. When the solar radiation interacts with the atmosphere, there are different processes, Rayleigh and Mie diffusion processes, and also absorption by the components of the atmosphere. So the solar radiation experiments some transformations. We get some beam irradiance, which keeps its directional character, and the diffuse irradiance, which comes to a given point from the whole sky, more or less. Part of the irradiance that reaches the Earth's surface is reflected and can also be reflected to our solar energy system. When we are talking about, CSP, concentrating solar power, we are interested in the beam irradiance because this is the component that we can concentrate. Diffuse irradiance cannot be concentrated with optical systems, so our solar resource will be this direct component. The beam irradiance is the component that produces shadows, more or less, and has a directional character. This slide shows the extraterrestrial solar spectrum in blue, and also the spectrum of the direct component in yellow and of the diffuse component in green. The sum of both of them makes the global irradiance, which is shown in this magenta color. As we said, the extraterrestrial solar spectrum can be approximated by the emission of a black body at 5500 Celsius, more or less. We can see that the direct component keeps still a lot of energy, a lot of power, and so it's a high quality energy resource. When we look at the processes in a clear day, in a day without clouds, a cloudless sky, we can see that the different components of the atmosphere absorb part of the radiation in proportions depending on the, well, for example, the air molecules, which with a more or less constant composition absorb 8% of the solar radiation and reflect to the space about 1% and 5% to the Earth. Dust and aerosols absorb and reflect in the different proportions depending on their composition, the composition of dust and aerosols. Water absorbs, mainly the main process with water is absorption of solar radiation in proportion to the water content in the atmosphere, normally measured by the relative humidity. And finally, in a clear day, we can have about between 83% and 65% normally of this irradiance reaching to the Earth. That means that we can have between about 1,100 watts per square meter and 600 or 700 watts per square meter in a clear day, in a day without clouds, depending on the conditions of the atmosphere, depending on the haze, on the dust and aerosol contents, on the relative humidity, and so on. On the other hand, the solar radiation, which is the resource, has some specific characteristics, like for example the different cycles, mainly the daily cycle and the seasonal cycle, which produces, for example, the day and night cycles, and the modulation of solar radiation during the day and during the year. We all know that we have at the maximum of solar radiation, it's normally, especially during clear days, it's near solar noon, and that the solar radiation decreases as we approach to the sunrise or to the sunset from the solar noon, starting from the solar noon. And the seasonal dependence of solar radiation is clear to all of us. Normally we have more irradiation, more insolation during summer months in the northern hemisphere, and less during the winter months, also connected to the duration of the daylight. We have to take into account these factors. We have to take into account also the low density of solar radiation that makes it necessary to concentrate solar radiation in order to increase the power density, and therefore be able to take advantage of the high quality of solar radiation. As we said, only the direct component can be concentrated. And another factor is the geography. Solar radiation depends clearly on latitude, mainly because of the optical path that the solar radiation has to travel in its way through the atmosphere. Normally, the higher the latitude, the smaller the less we have less solar radiation. And finally, there's an important fact that's a random component. In fact, the solar radiation is modulated by meteorological conditions and mainly by clouds. Clouds are the dominant factor regarding the modulation of solar radiation, and even more when we are talking about the direct component, because the direct component has a very clear characteristics, is close to or is similar to the clear sky value when an average typical clear sky value when there are no clouds, and is almost zero or zero when we have clouds. Of course, depends on the characteristics of the clouds. If we have very thin clouds, we may have some direct irradiance, but normally we have it's almost a digital value, all or nothing. And cloudiness depends a lot on the climatic characteristics of the site, so it's very important to take into account these characteristics. We can't rely only on latitude, although it's a good indication probably for the availability of solar resource, but we should analyze the climatic characteristics of the site to make a good assessment. Well, after this very brief overview of the characteristics of the solar resource, and especially of the solar resource for concentrating solar power, I will talk a little bit about solar radiation measurements. Mainly I will describe the most common equipment for measuring solar radiation, and I will do some considerations about them. In this picture we can see the solar radiation measurement station we have at the Civil Engineering School. This station has been measuring since 1984. It was in a different building. we moved to this new building in 1998, so it was from 1984 to 1998 at the old building, placed a few kilometers from here, and since 1998 this meteo station is located at the building, the labs building of the Civil Engineering School. Here we can see some of
Manuel,
the...
sorry.
Yes?
Yes? Manuel, sorry. Yeah, I think that your microphone is moving and we get a noise. So I don't know whether you could fix close to your mouth or something to avoid
I will
this
try.
background noise.
Is it better now?
Better? It's louder, but the sound was okay, but just something is moving or seems to be moving. So yeah, let's try in this new position. Thank you.
Okay, I hope it's better now. Well, in this picture we can see some of these measurements equipment, apart from typical meteorological equipment like an anemometer and thermometers for measuring air temperature and so on. We can see some pyranometers for measuring global solar radiation, global irradiance, pyrheliometers for measuring direct irradiance, pyranometer with a shadow band for measuring diffuse irradiance, and here we can see a sun tracker, two-axis sun tracker to mount a pyrheliometer, because this device, as we will comment immediately, requires two-axis tracking of the sun. We have also some pyranometer mounted on a tilted surface for research purposes and so on. Well, when we talk about solar radiation measurement, perhaps the oldest equipment, it's not properly a solar radiation measurement, but it has a lot to do with that, is the Campbell-Stokes sunshine recorder. This device was designed in the mid 1800s by Campbell, then modified by Stokes, and it's a very simple device that concentrates the solar radiation on a card, which in case of the sun is shining, if the sun is shining, gets burned, thus marking the sunshine periods. Of course, this is not precise at all. It's a very rudimentary instrument, but it's interesting because there are long series of sunshine duration all over the world, more or less, because of the simplicity of this instrument. And at least for statistical purposes, is it's an interesting measurement. Then we have the pyranometer. There are different types of pyranometer. I won't go into details. Pyranometer measures global irradiance. In case it's placed on a horizontal surface, we get the global horizontal irradiance. Here we can see a typical curve for global horizontal irradiance in a clear day. If we block the direct component, the beam component, using some kind of shadow disk or shadow band, we can measure the diffuse irradiance with the pyranometer. There are different types of blocking devices, discs, balls, or bands. The use of one or another depends, of course, on the characteristics of the meteor station, and in some cases models to correct the effects of the shading devices are required. And finally, we can see here a pyrheliometer mounted on a 2-axis tracker. This is a rather old 2-axis tracker because this is an electromechanical device similar to with a clockwork mechanism. But nowadays there are 2-axis trackers fully automatic which are computer controlled. The pyrheliometer measures the beam irradiance. This measurement requires 2-axis tracking, as I said before, and it's the recommended instrument for measuring direct irradiance. There are other devices. For example, there is a combination of a pyrometer with a shadow band. It's the rotating shadow band radiometer, which measures global and diffuse irradiance and calculates through different models, or by applying mainly the conservation equation corrected with some models, permits to estimate or to calculate the direct component. Anyway, the recommended instruments are normally these ones, or of this type. Here we can see different pyrometers with different shading devices too. For example, this is a band, a shadow band, and this is just a point blocking device. And well, the pyrometer measures broadband global solar radiance. Normally it's placed on a horizontal surface. We have to take into account that the response decreases as the cosine of the angle of incidence, although many pyrometers already include a correction factor for this effect. And well, the diffuse radiation is measured with a pyrometer with a shading device. Global horizontal radiation is perhaps the most readily available measurement in many places of the world. It's easier to measure than direct or even than diffuse because you just need to install it on a horizontal surface, make sure that it's really horizontal, and record the measurements. You should clean it as any other device, and we will talk about it a little bit later, but from time to time. But well, in principle, there are no moving parts, and that makes the measurement simpler. Also, the devices to measure global radiation are normally cheaper than those to measure direct radiation. The beam irradiance is measured with a pyrheliometer, as I commented before. The pyrheliometer has to be always properly aiming to the sun. There is a certain tolerance, an acceptance angle, but it's always recommended to keep it as perfectly aligned as possible. The direct irradiance is relatively easy to model because of the factor of the character we mentioned before, that it's almost, it takes the value of a clear day, whichever it is, when there are no clouds, and it's almost 0 or 0 when clouds are present, clouds are blocking the sun. The direct irradiance is sensitive to attenuation, and it's the main component under clear sky. The pyrheliometer, well, I won't go into details of the devices, but can be calibrated very precisely with an absolute cavity radiometer. Once we have a measurement station, we should make we should make sure that we are measuring correctly. For this, it's important to control the quality of solar radiation data. There are very different procedures, or many different procedures, all of them, to my knowledge, based on filtering the data. These filters basically compare with physical constraints, with other measurements, or with models. Perhaps the most extended quality control procedure is that proposed by the baseline surface radiation network, which I didn't include the reference here, sorry, but well, it's easy to find on the web a reference to that. And an important test in this procedure is the visual inspection by experienced staff, because well, an experienced scientist or engineer can identify different problems with the measurement equipment just by having a look at the curves of solar radiation, of the different components of the solar radiation. There are also other procedures. For example, I've given here the reference of a more exhaustive procedure proposed by IRRADIATION, or at least documented by IRRADIATION. Regarding the baseline surface radiation network quality test procedure, there are 5 tests. The first one is to compare it with physical possible limits, and the second one is to compare it with extremely rare limits, with values that are very seldom measured in the world. Then the comparison with other measurements. For example, if you have if you are measuring in the same station global horizontal diffuse on a horizontal surface and direct beam irradiance, then you can compare them because the difference between the global and the diffuse is equal to the direct on the horizontal surface, and then by calculating the zenith angle you can calculate the direct. If you compare this value with the value you are measuring with a pyrheliometer, you can get an assessment of your measurements. You can also compare with different models to see if the values you're measuring are within the range you expect. And finally, the visual inspection, as I mentioned, is a very important test. For example, I've presented here a very clear case, but well, it's just one case. In this case, we can see the beam component is the magenta curve, the global horizontal, and the diffuse. The diffuse this day shows very clearly a problem. I don't know exactly what type of problem, but it's very clear that these measurements are wrong. Probably there was a problem with the connection of the pyranometer to the data logger or something like that. The other 2 curves are quite good in principle. As you can see, this is the typical shape of the beam irradiance. In this case, it's almost 900 watts per square meter at noon, or close to that value. There is a certain asymmetry between morning and afternoon. This is normal in some places, and you can see also the global component, which is also almost symmetrical with respect to solar noon, as the direct component. In this case, these two measurements are correct, or at least they look correct. but the diffuse irradiance is clearly not correct. Other different problems are illustrated here. Very briefly, we can see some anomalies, abnormalities at certain times, which can be due to the reflection on a nearby element, whichever it is, or any other problem. But in any case, you can see that many days at this time we have this type of abnormality. Other very common problem is the problem with the time, with the measurement of time. Time in a good solar radiation measurement station, time should be measured. That means it's important to have a very precise time on the data logger, because solar radiation depends on time, and if you wish to later apply some models or make some quality control tests, you will get incorrect results if the time is wrong. For example, in this case, we can see that the clock of the meteor station is disadjusted, and as a consequence, the maximum value is achieved before solar noon. In this case, this is solar time. Solar noon, it's at zero solar time, and it's necessary, if the clock of the station is not correct, it's necessary to correct later the clock of the station in order to use this data properly. This type of errors have normally require a lot of work to correct, and lead to incorrect results in many calculations. Well, I've talked a little bit about measurement. Now estimation of solar radiation. You can estimate solar radiation using different types of models. These models, the use of one model or another, depend, of course, on the variable to estimate and on the available data and their characteristics. For example, it's possible to estimate the daily or monthly global horizontal or direct normal irradiation from sunshine duration, or it's very common to estimate hourly values from daily values of global horizontal radiation, and the estimation of global irradiation on tilted surface for different applications. And in our case, it's important to have the capacity or the capability to estimate the beam component from global horizontal irradiation. Normally, global horizontal irradiation, as I said, is it's easier to find the measurements of global horizontal irradiation in many places than to find DNI or beam direct irradiation components. So these types of models are used very commonly. There are other types of models. There are even models to estimate solar radiation from other meteorological values like temperature, relative humidity, etc. But normally, in our case, we are mainly interested in these types of models, in the estimation of the beam component from global horizontal radiation. We are also interested in that because, as we will see immediately, it's possible to estimate the global horizontal radiation by different procedures, even if we don't have measurements. For example, we can estimate the daily or monthly global horizontal radiation from sunshine duration from using angstrom type formulas like the one shown here. These types of model use the sunshine duration data, which are, as I said, available in many places all around the world. and in long time series, which is good from the point of view of statistics. I won't go into detail of this model. There are more complex methods to estimate, for example, direct normal irradiation from sunshine duration directly. For example, this one, which I developed in my PhD thesis a few years ago, and uses clear sky models combined with automatic reading of the sunshine duration periods to estimate the direct normal irradiation. And the results were quite good, but anyway, it's a complex procedure. And well, for example, perhaps the most widely used models are these decomposition models, which permit to estimate the beam and diffuse components from global horizontal radiation. We can start from daily or hourly global horizontal irradiation values and then apply these decomposition models, which relate the diffuse component, in this case defined through this diffuse index. The subscripts are missing, sorry, in this case, but this is KD, which is the diffuse index, and this is the clearness index, which is defined as the global horizontal irradiation divided by the extraterrestrial irradiation for the same period. And using these models, it's possible to estimate the daily or hourly values of the diffuse components, and by using the conservation equation, we can get the beam component on a horizontal surface, and then using the solar geometry calculation, estimate or calculate the beam component. As I said, these models are widely used, and the main problem with these models is that, of course, they use one only variable to explain, which is the clearness index, to explain the different atmospheric conditions. That's well, it's a strong simplification, but well, the results on average are good if the models are properly adjusted for the region where you are using them. This is, for example, an example of the comparison of different models of this type, the composition models. In this case, it's for daily values, and as you can see, different models give different results. This is a comparison we made in the frame of one of our studies, but well, as you can see, there are some differences between different models that, of course, lead to different estimations depending on which one you use. Another source for estimates are the satellite images. The use of satellite images to estimate solar radiation is based on the energy balance. The satellite has a sensor, and this sensor receives a signal from the Earth. If you apply the energy balance, the extraterrestrial solar radiance must be equal to the signal received by the satellite plus the radiation absorbed by the atmosphere, but plus the radiation absorbed by the Earth itself. The objective is to estimate the global irradiance, and therefore you have to be able to measure or estimate the energy absorbed by the atmosphere, and to measure or estimate the albedo, which is related with the energy absorbed by the Earth. This is the theoretical basis for this type of estimations. There are different procedures or different models to estimate solar radiation from satellite images, and Well, normally, at least the most frequent is to use geostationary satellites. In Europe, this satellite is the METEOSAT. An advantage of this of these estimates is that that they provide a global cover of certain regions of the Earth. When you use geostationary satellites, the information of these satellites is always referred to the same window, to the same region of the Earth. And other advantages is that it's possible to analyze past climate using satellite images of previous years. If we have satellite images since the 80s and we develop accurate models, it's possible to go to these old images and estimate solar radiation for those years. So it's possible to develop a time series for a good number of years. Another advantage is that since you cover a wide area with one satellite, you are using the same detector, the same sensor to evaluate solar radiation in different places. There are some disadvantages or problems, most of them related with the fact that you are not measuring solar radiation but brilliance, and for example clouds and some types of soils may have values of brilliance in the same range, and other problems related with the digital conversion. There are some other facts that you should take into account, but summarizing, it's important to be aware that when you use solar radiation values estimated from satellites, they are estimates based on models. They are not properly measurements. Of course, the models are every time better and better. They are getting more accurate models are being developed, and in my opinion, the accuracy of a global irradiance or irradiation, so global insolation estimates is quite good nowadays, for at least the case I know better for Spain, but I assume it's also good for other regions of the world. This estimates the accuracy or the goodness of these estimates may be different from one region to another region. But considering it globally, I would say that satellite estimations are a very interesting and quite reliable source of information for solar resource assessment nowadays, always taking into account that it's not a measurement. Satellite estimations rely on different types of models, physical and statistical models mainly. The purpose is always the same, is to estimate the global solar radiation on all the pixels of the image, and these types of models can be, there are statistical models, physical models, and some models that combine the characteristics or the methods of these two types. For the statistical models, normally what you do is to adjust them with parametric data measured on the Earth's surface, and you just adjust some types of models, regression models, between this data, this surface measured data, and the digital count of the satellite. These models are relatively simple and easy to apply, and they do not need meteorological measurements, but there are limitations because to adjust these models you need ground data, data measured on surface, and therefore they are not at all universal. If you adjust them with data from south of Spain, it's very likely that you get important errors when you try to apply them in England, for example. So this is it's important to adjust them properly. The physical models are based on the physics of the atmosphere, and well, they in principle they don't need ground data for adjustment, but they need as input measurements of different atmospheric components. We also have some databases and tools. Some of them are for free, and some of them are commercial products. I've listed here a few of them, which, for example, the HelioClim or the European Solar Radiation Atlas, PVGs, which are, well, I think all of them are public. Perhaps the European Solar Radiation Atlas is not, I'm not sure that you can, that it's for free, but anyway, you can find information on these web pages. Solemi, it's Solar Energy Mining is a company. I think it's a spin-off. I'm not, if I'm not right, and anyone knows it, please correct me. But I think it's a spin-off of DLR, and they provide, well, Solar Energy Mining is their name, and they provide services for solar resource assessment. In the United States, there is a public National Solar Radiation Database, which is, in my opinion, really good. One of the best solar radiation databases in the world, of course. And NASA gives also provides a free database of solar radiation from satellite images, estimated from satellite images, which is well, it's an interesting tool too. There are also commercial products like METEOROLOGICAL, which perhaps many of you already know, and which is a very, I would say, it's getting a traditional tool, and it's improving from version to version. Here, for example, we have the stations used for the elaboration of the National Solar Radiation Database in the United States. As you can see, it's a huge number of stations distributed all over the territory of the United States. There are different types of stations, and many of them with measurement of solar radiation, which is not very common. This National Solar Radiation Database provides typical meteorological years. In this case, the last version, TMY3, it's the last version. These are data sets of hourly values of solar radiation and meteorological values for a 1 year period. These typical meteorological years are used mainly for computer simulations of different solar energy conversion systems, and the procedures to elaborate these typical meteorological years are different. There are different procedures, but well, I won't go into details. For example, there's one procedure. It's the Sandia. It was developed by Sandia National Labs. You can find some information about this procedure in this website of the NREL, and there are also other procedures that can be consulted in the specialized literature. For example, in magazine journals like Solar Energy. Regarding the statistical characterization of the solar resource, first of all, why is it important to this statistical characterization? It's important because when you are developing a solar energy project and you are looking at, for example, the profitability of the project, you can't rely on the data from one single year or on data of the last year or even of the last 2 or 3 years, because although the climate of a given site is well, it's more or less constant, the meteorology is not, and the solar resource changes from year to year. These changes may be normally within ±5%, for example, but in some years you can have more differences. That's for a 1 year period, but when you go to smaller periods, for example months, you can have some months, for example in January, 1 month you can have almost zero solar DNI, direct normal irradiation, like this year in Seville, and other Januaries of different years you may have more than 100 kilowatt hours per square meter. So you're interested in the resource in the long term. Your project normally will be generating energy for 20-25 years, and you'd like to know what you can expect during this life of the project. Therefore, it's important to have a good characterization from the point of view of the statistics of the resource. For this characterization needs or requires long series of measured data, because in principle it's not. I would say it's not correct to characterize the resource from modeled data, from estimated data, because the characteristics of normally the results of the model show different types of bias, or the characteristics of the results differ from the reality. For this characterization, again, we can use as resources the sunshine hours, because there's a good availability of data. The problem is that they are not very precise, but they can show some kind of evolution of constants or trends in the evolution of the solar resource in a given site. The global horizontal, we have a better availability of global horizontal insolation for different places in different places of the world. In some other, we don't have measurements at all, and unfortunately there are few places where we have long series of dark normal of irradiance or irradiation data. The availability is very poor. Normally the series either are very short or they show a lot of problems, because measurement of the beam component is complicated because of the fact that you need an accurate tracking of the sun. And now with automatic trackers it's easier, but before with trackers that required periodical adjustments it was more difficult, and the errors were common. On the other hand, the statistical distribution of the solar radiation depends on the aggregation period. For example, the instant values of direct irradiance have a distribution totally different from the monthly or yearly values. For sure, the instant values of solar radiation in general don't follow a normal distribution. They follow different types of distribution. But when we go to monthly or yearly values, global irradiation shows more or less a normal distribution. It's commonly accepted that, that the distribution of these monthly and yearly values is close to normal. For the case of the DNI is different. The distribution of yearly values is not normal, for sure. Some authors propose that it could be similar to a Weibull distribution, like in the case of the wind resource. But in any case, it's something that it's under discussion and it's being analyzed in different studies. Of course, if you know the distribution, it's easier to get a good solar resource assessment. Well, finally, I will give some recommendations for the good solar resource assessment for a CSP project. First, I would say that the first step is to once the site has been selected, is to estimate the solar resource from all available data, from all available information. But it's important that this estimation be made by experted people, by experted team, because other way it's difficult to, well, it's easy to make significant errors. Even for an expert, it's difficult to make a good estimation from this data. So try always to find the help of an expert. What kind of information should you look for? First of all, surface measurements, if available, very close to the site, that's the best, or in the surroundings. The surroundings may be in a radius of a few tenths of kilometers. If it's closer, it's better. If the station is not so close, it's farther, or it's worse. But still, is a source of information. Depends this distance. Or the distance where you should look for depends also on the characteristics of the site, whether it's just very flat land or the orography is complicated, etc. Then satellite estimates from databases, be it public or commercial, are also a good source of information. Sunshine hours, if available from a meteorological station in the surroundings, can be of help. And if you don't have any other information, the qualitative information is a first approach. Qualitative information means talking with people, trying to find different types of records. Sunshine hours is good, but any other type of information about the climate of the place, of the site, is of interest. Second, if you have already selected the site and you think it's a good place, it's important to set up measurement station site, measurement station with a data logger, and at least if it's a CSP project, I would recommend a pyrheliometer with its corresponding tracker, and a parameter for global parameters for global and diffuse irradiance measurement. If there are cost restrictions, perhaps you could set aside the diffuse measurement, or well, depends. The pyrheliometer and the tracker are normally the most expensive components of the METEO station, but also for a CSP project, the DNI measurements is the most important. And the METEO station should also include some wind temperature or some other meteorological measurements, wind temperature, relative humidity, etc. It's very important to maintain the station properly, and that means, among other things, a frequent cleaning of the instruments. Other way, the dust, the dirtiness affect the measurements. Normally you get reduced reduced readings. I mean, you normally measure less than you should if the instruments are not clean. So it's important to maintain the station properly. Of course, you should perform a quality control of measured data. This quality control should be performed as frequently as possible so that you can detect possible errors as soon as possible and correct them, because well, it's important to get a series of measurements with as few gaps as possible, and and then once you have your measurement station there and you have been measuring for a certain time, perhaps well, some authors recommend at least 1 year of on-site measurements. It's the time to compare the estimates with these measurements and to make a good assessment of the solar resource, normally of the direct and global insolation. You have to take into account that 1 year is not significant from the statistical point of view. So if you have long-term estimates from satellite, you should combine them and with the measurement, analyze them carefully to make a good assessment. Again, this analysis must be made by experts. It's important to rely on experts for these types of work. Finally, normally it's required by the banks or even by the engineering to elaborate design years from measured data. These design years may be typical meteorological years, like the one we have commented before. They are time series of 1 year of hourly or 5-minute or 10-minute or 15-minute values, and depending on the type of assessment you need for the project, you may require a typical meteorological year or the average year, the P50. That's the central value of a normal distribution. As I said, direct has not a normal distribution, so this series may be different. Or in some cases the P75, percentile 75 or 25, etc. That depends on the requirements of mainly of the banks, which try to make sure that they are lending their money to a project which can return it on time, certainly. These are some recommendations for a good solar resource assessment. I hope this introduction to this topic has been useful to you. In principle, this is all from my side. I thank you for your attention, and well, I think perhaps we will have some time now for questions. Thank you very much.
Okay, Manuel, thank you very much. Another very interesting presentation, and we realize here how important is the topic of solar assessment, especially when you're close to make a project, and then project finance and banks require minimum reliability on what's going to happen in the coming years. So I would like to take advantage on this and send some questions on behalf of a banker. So from a lender's perspective, variability of solar data is more predictable between P50 or P90 assumption compared to wind data. Do you have any feedback on this? Thank you.
Yes. Well, I agree with this with this affirmation. Solar radiation is more predictable than wind, without any doubt. Solar radiation depends clearly on latitude, for example, depends on climatic conditions, and the variability of solar radiation is clearly, well, in the long term, the variability of solar radiation is clearly less than that of the wind. So I would say that that it's clear that solar radiation is more predictable than wind, and DNI too.
Okay, very well. And then the second question. So it's better to have at least 1 year DNI from the actual site together with 10 to 15 years of global irradiation data. Having said that, because it's not often possible to obtain direct normal irradiation data from the actual site, synthetic calculations have been used based on global irradiation data to assume direct irradiation data. This has been represented today. So the question is, how accurate can such synthetic calculations be? And is this a generally acceptable method? Again, I ask this question on behalf of a banker. So, so this is a banker who asks the question. Thank you.
To give a good answer for both the banker and the developers. Well, yes, it is possible to, of course, it's possible to calculate or to estimate DNI from global. If you have 10 to 15 years of global horizontal irradiance data, measured data, it is possible to make estimations with good accuracy. I would say that provided that the measurements are good and that you use the appropriate models, the accuracy or the error may be less, normally less than plus minus. I would say it would be between plus minus 5 and plus minus 10%. Depends on the models you use and on the characteristics of these models. A generally acceptable method, I would say that the method commonly used, that it's similar to the one, it's basically the one I have presented. That's to use the composition models and estimate the beam component from the global, DNI from global. It's an acceptable method. It's probably not optimum, but it's acceptable, and it provides reasonable accuracy. You have to take into account that measurement is complicated, and you can have errors of plus minus 5% for sure in measurement. So I would say the errors with these models are not bad, are acceptable in general. But you have to use the appropriate models.
Okay, very well. So next question from Dan. Once you have 1 year of on-site data, how do you combine with the long-term satellite data? Monthly regressions with concurrent data or monthly ratios? Thank
you. Well, depend on the information you have. If you only have 1 year of on-site data and you have a long-term satellite data, one thing you can do is to estimate. Well, normally the satellite estimations are good for global. When we are talking about DNI, you have to use similar models to estimate direct from global, And then if you are doing it from satellite, you have two modeling steps. One of them from satellite images to global, and the other one from global to direct. So one thing you can do with your measurements during 1 year is to check, if possible, the goodness of the estimates of direct from global for the satellite data. If you don't have, if you only have the long-term estimation or estimate for global irradiation, then then you can use models to based on measurements to estimate the direct and check if possible with this data. Monthly regressions, I wouldn't do that, or monthly ratios. It's very, the variability from month to month is very important, and if you only have 1 year, it's difficult. I don't know if that's if I've answered to the question, but well, that's what
Okay,
I can say.
Okay, thank you. We will leave Dan to further precise. Very well. From Rene Martinez from Chile, could you recommend a time window between each measurement from the data logger point of view? Thank you.
Well, if I understand well the question, it's a time window or the time between measurements, or the recording.
For the time step, yeah.
Yes, the time step. Well, depends on the type of data logger and of the function, of the purpose of the station. If it's a station for, we could say, research purposes, for scientific purposes, then it's the shorter, the more frequent, the greater the frequency, the best. But if it's a station that it's isolated somewhere in the country, I would say that it's enough to record the data every 10 minutes or 5 minutes. Depends on the memory of the device, depends on the type of connection. If it's for solar resource assessment for a project, I would say 10-minute data are good enough. 10 minutes, 5 minutes.
Okay, very well. Thank you very much. So another question, interesting one. How is climate change impacting solar radiation? I don't know whether it's been assessed, or I think it's a too short period of time to observe new trends. But if you have any additional comment, thank you.
Well, it's a very interesting question. I don't think it's a too short period of time, because climate change is probably occurring since a few years already. But I'm sure there are people looking at this. I would say it's difficult, because climate change, we have to see it in the long term, and the effects of climate change may be very different. For example, some people say that this strange weather in the south of Spain during this year has to do with climate change. We have had 4 months of cloudy and rainy weather, what it's really unusual. But at the moment, it's difficult to say whether it's so or not. I think we have to wait, or perhaps there are some people looking at that and they already have had reached some conclusions, or they had some ideas. At the moment, I cannot answer clearly to this question. Sorry.
Okay, very well. So next question, could we rely on data from METEOROLOGICAL to design a CSP plant with a reasonable accuracy? Thank you.
difficult to answer to. I would not rely only on metronome. For a first approach, it's a good information, but metronome, in my opinion, is an excellent tool. But the accuracy of the values provided by metronome are very site dependent. In the last, for example, when I started to use metronome, I think the models to estimate direct from global were not very precise, at least for Spain. Now they are much better, but in some places I've seen some results that well, they sound strange to me. So depend. I think you should look at other sources and compare. But for a first, as a first approach, they are good, especially the global values. The direct, well, depend a lot on the region and so on.
Okay, very well. So another question: is there a map of direct irradiance? Is there anything existing on this resource? Thank you.
A global map of the world. There must be some some types of maps. I don't know what are the basis for those maps. I've seen some global maps. Normally, they are based on satellite images and then on the use of models. The question asks for direct irradiance, watts per square meter. Normally, these maps are of global insolation or direct insolation or irradiation energy, watts-hour per square meter. There are some, but I don't remember exactly the references. And as I said, most of them or all of them are based on satellite images. One thing is that yes, excuse me, Fernando. One interesting thing is that in some places or some companies or institutes are developing geographical information systems where they integrate information of solar radiation. And if they have a wide geographical coverage, they will become very interesting tools for planning, for CSP planning.
Okay, very well. So another question: how often do you need to calibrate your apply? I guess this is a brand of pyranometer or heliometer. Thank you.
Well, it's recommended to calibrate them at least to at least compare them at least once a year. But well, there are specific recommendations from the manufacturer normally. But I think once a year is reasonable to calibrate them, or if you have a good instrument and good materials and methods to compare them with a reliable instrument, you can also do that from time to time, but at least once a year.
Okay, very well. So now it's time to adjourn. This was the fifth last session on this CSP training module. We have been delivering for 2 months now in 5 sessions. So hope this was interesting and also useful for you and for your jobs. Well, taking into account the fact that you've been more than 1,700 to be registered to the course following directly by this connection or indirectly recordings and slides, we'll definitely try to complete these modules with well, more in-depth sessions, probably on market, maybe on special applications like desalination. Maybe we will be inviting other solar assessment providers to do also presentations. So from here, you're invited to in touch with me to offer your contributions, and we will probably doing something by the autumn or winter this year. I mean, by October, November, as there are people from everywhere in the world. So thank you very much, Manuel, for your deep knowledge, for your time, these comprehensive presentations. Hope we will be further in touch, either with me, but also with this huge community of practice that we have constituted. Well, I give you the floor to say the final words. Probably talk to you soon in this webinar program. Thank you, Manuel, and I give you the floor.
Okay, Fernando, thank you very much. Thank you for giving me the opportunity to give this series of seminars, of lessons, and well, I hope it has been interesting for all of you. Thank you very much to those of you who have attended this seminar and the other sessions too. And well, just tell you that you can find me. Some of you have sent me some emails asking for more informations. If I have not answered, I'm sorry, but I will do it for sure. I have been very busy these days, but I will answer you. And if any of you have any question, you can any further question, you can send them to me by email. Well, nothing more to say. Just again to give you to thank you for your interest, for your patience, and I hope just it has been interesting for you. Thank you very much. Goodbye to all of you.